Hello friends, this is Sushrut Tendulkar and welcome to my YouTube channel. In this tutorial, we're going to learn how to build a simple neural network using PyTorch. We'll use this neural network for predicting the digits of MNIST dataset. Let's get started. Let's get started. So we'll broadly cover this entire thing in 6 different steps. We'll first import the libraries. We'll import the MNIST dataset. We'll understand the dataset. We'll design the model using PyTorch. We'll train it and then validate the results. So let me go ahead and start importing these libraries. Let me now import the MNIST dataset. We're defining a batch size of 64 here, and train dataset and test dataset separately are defined, and we're importing this using the datasets package. We're saying that train is equal to true, that means training dataset will be loaded here, and train is equal to false, so test dataset will be loaded here. And we are storing both of them in a folder called dataset. And we use a argument transform, which will transform this data into a tensor. So that is the requirement from the PyTorch library. Then we use a data loader method or the package from PyTorch. That is something we have imported here using torch.utils.data. So that will, as it's defined here, gives us easier data management and creates mini batches. So basically we'll train the entire neural network in a batch size of 64 instead of training all of them together. So we'll define a data loader class here, and then we pass in these arguments and then store them in 2 corresponding variables. So when you're doing it for the first time, it's going to take some time to download the data, but I've already done this, so it completed the task quickly. Now let's understand the data. What is MNIST data? MNIST data is collection of handwritten digits along with the corresponding labels. So our input will be the image, and we are supposed to build a model that's going to predict the label of it. So whatever we have downloaded here is collection of images as well as the labels, and we have stored them separately into different variables, train loader and test loader. Now how does the data look? So if I just print the train loader, it doesn't print the actual data, but it loads the data loader object. So we cannot access the data directly because train loader yields the data when we access it or when we request it through a for loop or something. So let's read the data here, and let's see the data from the train loader. So we can see that each entry here is of size 64 by 1 by 28 by 28. So here we can see that image is of size 28 by 28 and it is in the batches of 64. So each entry is a collection of 64 images with a size 28 by 28. We are also printing the labels here, which is of size 64. That means for each bunch or each group of users there will be one label. So here we have 64 images, so we have 64 labels. So similarly it's collection of all the images broken down into a group of 64. So let's see one of them. So let me just add a break statement here to print only one value. So it's 64 by 1 by 28 by 28. And for using this in our model, we need to convert this into a linear array of 64 by, or we have to convert this 28 by 28 square matrix into a linear array. So how do we do that? So we can use this function called view and we can reshape it. So how does it look? This is how it originally was, and this is the label. and now it became 64 by 784. So 784 is 28 by 28. So now we have 64 rows and 784 columns. So one image is converted into one row, and so there are 64 such image pairs. So I've added a break statement here to print only one set of images. Similarly, let's see what is there in the test loader. So whatever you have seen so far is from the training set. So now we are loading the data from the test set. So test set is exactly like the train. So basically, whenever we want to test our model, we have to convert this into 64 by 784 format, and then we can use it. Now let's start designing the model. So this is how our model is going to look like, or this is the architecture of the model. The input layer has a size of 784. That means it can accept data with 784 features. So that gets converted into layer with 128 units. That gets converted into a layer with 64 units, and finally output layer of size 10. So here each 10 corresponds to 10 different digits, each corresponding to the probability of the image belonging to one particular class of digit. So from there we pass it through loss layer, or which is cross entropy here. So this is basically going to calculate the actual predicted value and the actual value, and then use that for backpropagation. So I've already covered a high level overview of how the error function works and the backpropagation work in a separate video. If you have not watched that, you can watch that for getting a better understanding. Now again, if you think that there is only one training example, so here we have taken a group of 64, but imagine we have only one training example. So what we would do is we convert this 28 by 28 image into one single dimension image of 784 units. So 1 by 784 is the input. That gets multiplied with 784 by 128. So this is the hidden layer weight matrix, or the parameters. So what you get out of this is 1 by 128. So that's exactly what is given in the hidden layer. And 1 by 128 gets multiplied with a hidden layer parameters of size 128 by 64 to get the output 1 by 64, that is here. And 1 by 64 gets multiplied with the parameter of 64 by 10 to get, or to give the final output of 1 by 10. Hidden parameters are the ones that get updated on every backpropagation process. Now you can build this model in a couple of ways. So the first one is through a class. So what do? We define a class here and inherit the properties from nn.module. nn is already defined in Torch, so we just import that. And then we define an init function and a forward propagation function. Within an init function, we call this super function and pass this value to the parent function. And what the important part here is the how do we define the layers. So we need 3 layers here. Self.hidden will define a linear layer which takes 784 as input and produces 128 as output. So 784 is the number of features, or number of hidden features, or sorry, number of input features, and we are not talking about the number of training examples. So it can be one training example, 2, 10, 100 or 1000. So that we can define while we are training it. But for defining the model, we can just specify the number of features. So you can imagine 1 by 784 or 2 by 784. And similarly, the output layer will have 128 units. Again, number of training examples, we are not defining it here. So basically, if it is 100 by 784, this layer will have 100 by 128. If it is just 1 by 784, this will be 1 by 128. So that's how we should read it. And the output of 128 goes to the second hidden layer. Again, that will not consider the number of training example as one of the input feature here, one of the input for this function. It only requires number of features. So it will take 128 and produce 64. And similarly, we have output layer that will take 64 units as input and produces 10 as output. We also define two more functions. One is relay activation. Relay activation restricts the values between 0 and greater than 0. So whenever value goes to negative, it will stop that and makes that as 0. And then we also define a softmax function. So that will take the probabilities of the digit and outputs the one with the maximum probability. And then you have a forward layer or the function that will performs all the matrix calculation. So first it will take values to hidden, and then it will call the ReLU function, then pass the value to hidden 2, and then calls a ReLU function, then outputs, and then softmax function. So this is one way of defining a model. And the second way is using the sequential class that is defined within the neural network. So we just create an instance and then pass these as values. So this looks pretty straightforward. You just define the linear layers and you define the corresponding input features and the output features, and then pass it through a ReLU, then again the second layer, then ReLU, then the linear function, and then finally the log softmax. So this is the second way of defining it. So for this tutorial we're going to use this technique here. So let me go ahead and then define it. So our model is ready. Let's define loss and optimizers. So every model requires a the loss function to be defined. Again, in my introduction to a neural network tutorial, I have covered this at a very high level. So if you have not watched that, you can watch that for getting better understanding. So here we are defining negative log likelihood as the loss function. So let me define that. And also I'm defining an optimizer function. So in this case, we are using SGD with a learning rate of 0.003. So what is negative log likelihood loss? What is SGD and how do they work? Probably I will cover that in a separate series of tutorials. Alright, so now we have defined the model, we have defined the criteria and the optimizer. So let's start training the model. So here I'm taking an epoch of 5. So 5 times it's going to run through all the training examples. And if you're using the model defined as a class, so we'll have to initiate it. So I'm not going to use that technique. I'm just use the second technique. And I'm iterating through all the 5 epochs here, and defining running loss as 0. So which I'm going to increment for every loop. And I'm looping through each of the images in the train loader. So images and labels. So I'm going to flatten this into 784 vector, how we defined a little earlier. So we're going to take each image and then reshape into the size of 64 into 784. Next, we need to next we need to do optimizer.zeroGrad. So PyTorch accumulates the gradients on subsequent backward passes. So that's why we need to set it to 0 for every loop. If we are training a RNN, then this step is not needed. But for this kind of serial forward propagation, we need to set the gradients to 0 for every loop. And then we pass this image, that is the training example, through this model. So it will pass through all the layers and produces the final output, which is the softmax output. And then we have criterion defined here, which is negative log likelihood. So it will calculate the difference between the actual output and the calculated output and store that as a loss. And finally we call loss.backward here. This is going to do the back propagation. So this will calculate the gradient on its own, so we don't have to do anything. And finally we call this optimizer.step. This is something that performs a parameter update based on this loss or the gradient that is calculated here. So similarly we're going to update these here for every iteration, and then we're going to print the results. So let me start this. Let me run this one. For every epoch it's going to print the loss, and we should see that for every epoch the loss going down or reducing. We see that the loss is reducing, and yeah, it completed the 5 epochs and then the loss is 0.59. So probably if you run it many number of times, the loss is going to go further down, but we'll stop at 5. So once training is done, let's validate the results. So let me define 3 variables here, one for storing the prediction, one for storing the test labels, and one for storing the test image. So we'll loop through each of the test loader again. So this is also collection of 64 by 748 images. So we're going to pass it through the model, and then we're going to store the prediction into this prediction variable. We're going to store the actual label in test label, and we'll store the actual image also for our own understanding. So let me run this one. So it has run on the test data set now. Now let's see the first image of the test set. So it is 64 by 784. Now let's, instead of viewing all the 64 examples, let's pick up only first example from that, and we'll reshape it to 28 by 28 and then pass it through plt.imshow. So we should see the first image. So it looks something like 6. And let's see what is the prediction for the first example. So it's a collection of 64 images, as I said, and the first example is 6. So the model has correctly predicted this as 6. And what is the actual value? Actual value is also 6, right? So similarly, if you can print the second one, so it's something like close to 0, but the prediction says it is 5, but the actual value is 0 here. So similarly, we can go on comparing the each and every value. So let me check the third one. So it's 4, prediction is 4, and the actual value is also 4. So let me compare these two sets and then calculate the sum. So it says 51. So out of 64, it has correctly predicted the values for 51 digits. So model is working pretty well. So probably the accuracy is going to increase if we increase the number of epochs. We just trained it for 5 times, and if we increase, definitely this 51 gets closer and closer to 64. So that's how we define a simple neural network and use it for predicting the MNIST digits. Well, that's it for this video. Thank you so much for watching. Keep learning. Bye bye.